Alright, so this video is going to be on 9.3 Gibbs free energy and thermodynamic favorability. And so what we're going to talk about is Gibbs free energy and how to determine whether or not a process is going to be thermodynamically favorable, as well as how entropy and enthalpy are going to both affect this favorability. So what is Gibbs free energy? So basically, chemical reactions proceed until equilibrium is reached. We already know this. And so some are going to favor the reactants, some are going to favor the products. And basically what Gibbs free energy is going to tell us, and the Gibbs free energy change, is going to describe whether a reaction is thermodynamically favorable or unfavorable, whether it's going to be able to happen or not. And so changes that are thermodynamically favorable are going to proceed to equilibrium without external intervention. They can move forward, they can go. The common misconception here is that just because a reaction can proceed and is favorable, this does not mean that it happens quickly. So rates are different, and rates are going to be determined by activation energy. And so that is not what we're talking about. So we could have a reaction that is favorable that still is happening so slow that we can't perceive it to be happening because that activation energy is so large. But it can happen. So the Gibbs free energy change for a chemical process in which all reactants and products are present in standard state. So we got pure substances, 1 molar solution, gases at 1 atmosphere, is going to be given the symbol delta G with the degree sign. So the value of delta G cannot be assumed based on a given G value under given conditions. It is going to change. So even if Gibbs free energy is less than 0 under some conditions, that does not imply that the delta G is negative and vice versa. So the standard Gibbs free energy change for a physical or a chemical process, so again, this can happen for physical or chemical changes, may also be determined from the standard Gibbs free energy of the formation of the reactants and the products. This is going to be very similar to what we just did with entropy. And so delta G is less for when delta G is less than 0 for a process, it's said to be thermodynamically favored. So let's talk about why that is. So if we think about it, the delta G of the reaction, the overall reaction, is going to be the sum of the delta G of the products minus the sum of the reactants. So if this value is negative, that means that the products require less energy than the reactants, and so that means that it's going to be thermodynamically favorable. So what I want you to do is I want you to think of this table. So if delta G is less than 0, so it's a negative number, this means that the reaction is going to be thermodynamically favorable. When the delta G is greater than 0, so we have a positive number, it's not thermodynamically favorable because that is meaning that the products are requiring more energy than the reactants, and so it's not going to go spontaneously. And then when delta G is equal to 0, this is when we're at equilibrium. And so the rate of the products is equaling the rate of the reactants. And so we have a delta G of 0. So let's go ahead and kind of put this in terms of multiple choice example. So we have the decomposition of H2O2, and that's represented by the equation above. A student monitored the decomposition of a 1-liter sample of H2O2 at a constant temperature of 300 Kelvin and recorded the concentration of H2O2 as a function of time. The reaction is thermodynamically favorable. The signs of delta G and delta S for the reaction are which of the following? The first thing you should notice is that it says the reaction is thermodynamically favorable. I just told you if it's thermodynamically favorable, delta G has to be negative. So automatically now you have a 50-50 shot of getting it right. So now let's talk about delta S. Well, for delta S, remember you're going to look at the reaction and look at the phase changes. We're going from an aqueous solution to gas. So if we're going from an aqueous solution to gas, delta S is going to be positive. So our answer should be B. So let's go ahead and read that out all written out. So because the reaction is thermodynamically favorable, okay, again in the prompt, delta G has to be negative. In the equation, a gaseous product is formed from an aqueous reaction, or an aqueous reactant. So this indicates that delta S is positive, so entropy had to increase. And so that's kind of how you're going to look at these types of problems. And again, remember, multiple choice questions, they're going to be more conceptual like this and less like having to calculate very difficult math numbers. So here's an example FRQ. So the hydrate, CaSO4, can be heated to form the anhydrous salt, CaSO4 solid, as shown by the reaction represented above. Using the data in the table below, calculate the value of delta G in kilojoules per mole reaction for the reaction at 298 Kelvin. So again, for this equation, all you have to do is remember that the sigma, or the sum of the products minus the sum of the reactants, and you have to take into account the coefficients. So if you plug your numbers in, again, make sure that you understand where these numbers are coming from, but we have products. So we have products here. Okay, I got it from the table. And then we have reactants, and we subtract the two. And so if we do this, so we're going to get 18.22 kilojoules per mole. So now let's talk about thermodynamic favorability. So it's sometimes necessary to consider both the enthalpy and the entropy to determine if a process will be thermodynamically favored. So if the enthalpy and the entropy values can be predicted or determined at a given temperature, then we can also calculate the standard Gibbs free energy change, and we're going to use the equation on the screen. So delta G is going to equal delta H minus T delta S. So we need the enthalpy, the entropy, and the temperature. And if we have all three of those, we can calculate the Gibbs free energy. So let's go ahead and break this down. Now, if you can memorize this table here, it's going to make your life a lot easier. But better yet, let's go ahead and see if we can understand this table. Now, I'm going to give you a hint here. If you still need help with this concept, Khan Academy has a really good video, and I've linked it in your notes. Okay, so it's going to be right here. If you click on it, it will take you to the video. But in general, the temperature conditions necessary for a process to be thermodynamically favored, which means that the delta G is less than 0, can be predicted by the signs of delta H and delta S. So what you have to remember is this equation. And if you remember this equation, you can predict which numbers are going to be negative and which numbers are going to be positive. So let's go ahead and look at this first scenario right here. So if we have a negative delta H, so we have a negative here, and a positive here, that means we're going to have a negative number subtracting a bigger number, and so this is always going to be negative. And so it doesn't matter what the temperature is, both of these numbers are going to cause this delta G to be negative, which is going to be thermodynamically favored. And so that's why at all temperatures, if you have a negative delta H and a positive delta S, that means that you're going to have a thermodynamically favored reaction. Doesn't matter what the temperature is. Now, if you have a positive delta H and a negative delta S, think about what that's going to do. That's going to be a big number here, and you're subtracting a negative number. So if you're subtracting a negative, that's going to be a positive number. It doesn't matter what this T is. So with a positive delta H and a negative delta S, it doesn't matter what the temperature is, it's never going to be favorable. Now if we have a positive delta H and a positive delta S, well, if this number is big, what we need is this concept to be bigger. So we need the delta S times the T to be bigger than this delta H to get a negative number. And so that means that if we have a really big T, then this number, okay, T delta S, is going to be bigger than the delta H, and we're going to get a negative number. So at high temperatures, if both delta H and delta S are positive, at high temperatures, it's going to be thermodynamically favorable. Now, the last scenario is we could have negative for both numbers. If we have a negative delta H and we're subtracting a negative, okay, so if we have a negative here and we're subtracting a negative, so that means that we're adding this. So if we're adding this, we want this T delta S to be as small as possible because we don't want it to overcome this negative delta H. And so that means that if we have a low T or a low temperature, then this will be thermodynamically favorable. So if they are both negative, at low temperatures, they're going to be thermodynamically favorable. Again, it's better to understand this concept because once you understand it, you can make a prediction about what's happening with delta G. So let's go ahead and write that out with what I kind of just said. In cases where both enthalpy and entropy are favorable, no calculation of delta G is going to be necessary to determine that it is thermodynamically favored. Okay, so they might try and get you to waste time in doing the calculations. If you can just think it through, you should know that this is going to be thermodynamically favored. And so then in cases where both enthalpy and entropy are unfavorable, no calculation of delta G is necessary to determine that the process is thermodynamically unfavored. Again, think about it. Think what you have and figure out if it's going to be favored or unfavored. So let's go ahead and look at an example. So we have H2 plus F2 is going to give us 2HF, and we want to find the delta G of the reaction. Well, let's say that we have the delta H and the delta S of the reaction given at 25 degrees Celsius. And so what we're going to do is we're going to plug it into our equation. So remember, delta G is equal to delta H minus T delta S. Now, one thing is our T is in Celsius, and we have kilojoules here and joules here. So you have to really pay attention to units in these types of problems. So Kelvin is going to be Celsius plus 273, so an easy conversion for that. And then what I'm going to do is I'm going to convert my 13.7 joules per Kelvin reaction into kilojoules really quick by just moving my decimal over 3 times. Again, kilo means 1,000, so 1, 2, 3, that's where I got this 0.0137 from. And so now I make sure that all of my units are matching up. I got kilojoules and mole reaction, I got Kelvin, I got kilojoules, I got Kelvin, I got mole reaction. And so what I do now is I just kind of calculate it, and you're going to end up with negative 541.3 kilojoules per mole reaction. So basically what this means is that the forward reaction is going to be thermodynamically favored. So if we put H2 gas and F2 gas in a container, the forward reaction to create 2HF gas is going to be favored. Now here is an example multiple choice question. So the elements K and Cl react directly to form the compound KCl according to the equation above. Refer to the information above and the table below to answer the questions that follow. It's observed that the reaction producing KCl from its elements goes essentially to completion. Which of the following is a true statement about the thermodynamic favorability of the reaction? Well, a negative delta H should tell you that that is going to be favored. So we have a favorable delta H. But let's go ahead and look at the enthalpy of the reaction. The enthalpy of the reaction, we have a solid and a gas going to a solid. And so the enthalpy of the reaction is actually not favorable, okay? So that's going to be a negative delta S. And so a negative delta S is unfavorable. So right here, we know that the delta H is going to be driving this reaction forward because that's the only favorable one that we have. So what we need to do is we need to look for an answer choice that's going to tell us that. So A, the reaction is favorable and driven by the enthalpy change only. So that is true. Our delta H is the only favorable one here, and that's driving the reaction to completion. But let's go ahead and double check the rest of them, make sure they're wrong. So the reaction is unfavorable and driven by entropy change only. So it's not unfavorable, it's favorable, it's going to completion. So that one's wrong. The reaction is favorable, okay, so right, and driven by both enthalpy and entropy changes. Well, our entropy change is negative, so it's not driven by that. That's unfavorable, so that one's not right. And then the reaction is unfavorable. I already know that one's not right because it is favorable. And so the correct answer is going to be A. The reaction is favorable and driven by an enthalpy change only. Because remember, think about that equation. That delta H is negative, which is a good thing, but our enthalpy is also negative. So if we go back to that table, you'll see that when we have a negative delta H and a negative delta S, that it's going to be favorable at low temperatures. And so that's what's kind of going on here. So here is what I just said typed out. So because delta H is negative and delta S would also be negative due to the formation of the solid product from the gaseous and solid reactants, the favorable enthalpy change drives this reaction to completion, meaning that it is a thermodynamically favorable reaction. So now here is a long example FRQ. So we got a student investigates the reaction between Ag solid and HNO3 aqueous, represented by the equation above. So first off, it wants you to predict the sign of the entropy change delta S for the reaction and justify your answer. It wants you to use the information in the table below to calculate the delta H reaction, the standard enthalpy change for the reaction in kilojoules per mole. And then based on your answers to part A and B, is the reaction more likely to be thermodynamically favorable at 25 degrees Celsius or at 95 degrees Celsius? And then a student runs the reaction using a 3 to 4 mole ratio of Ag to HNO3. Suggest a method the student could use to isolate the solid AgNO3 from the other products of the reactants. So let's go step by step. So part A. Predict the sign of the entropy change. Again, just look at the phase changes. We go solid and aqueous to aqueous and gas. You should realize that gas is going to be a positive entropy change because we have a mole of gas in the products side. So the entropy change is positive because the reaction has 1 mole of gas in the product and none in the reactants. So again, just look at your phase changes. Most of the time that's going to tell you what's happening with the entropy. So part B, use the information in the table to calculate the value of delta H of the reaction, the standard enthalpy change for the reaction in kilojoules per mole. So again, what you're going to do is you're just going to go products minus reactants. So you're going to add up all the products, add up the reactants, subtract them, and you're going to get your change in H. When you do this, you should get 43 kilojoules per mole of reaction. So now you should recognize that the delta H is positive. So let's go ahead and think about this. So based on your answers to parts A and B, is the reaction more likely to be thermodynamically favorable at 25 degrees Celsius or 95 degrees Celsius? So what you need to do is you need to think about this equation again. And so previously, we have the fact that we have a positive delta H and a positive delta S. So if you look here, we have a positive delta H, which is bad, okay? We want this delta G to be negative. So if this positive delta H is there, what we need is we need this to be as big as possible so that when we subtract it, it overcomes this positive delta H. And so we know that this delta S is positive, which is good. So what we need to do is we need a high temperature to make sure that this T delta S can overcome that positive delta H. So basically, the reaction is going to be more likely to be favored at a higher temperature. So the answer is going to be 95 degrees Celsius. At the higher temperature, that T delta S is larger and more positive. And so thus, when T delta S is subtracted from that positive delta H value, the delta G is going to be more likely to be negative when you're subtracting a larger number. Now, if you're still a little confused about this, Khan Academy again has another worked example problem that is exactly like this. It's just different numbers and a different reaction. So if you're still confused, go ahead and check that video out. And finally, this last question, which I think that you would overthink a little bit if you guys were doing it on the test, but go ahead and think about it. So a student runs the reaction using a 3 to 4 mole ratio of Ag to HNO3, suggests the method the student can use to isolate solid AgNO3 from the other products in the reaction. Well, okay, it's giving you a mole ratio to try and confuse you. You're going to be like, well, what the heck do I use the mole ratio for? Just ignore it. Okay, look at what you're getting. So you have an aqueous AgNO3, you have a gaseous NO, and you have liquid water. But it's asking you, you want to isolate the solid AgNO3. Well, how do you isolate a solid if we have a gas and a liquid? So basically, and especially if that gas is water, or if that liquid is water, so the gas is going to be released anyways unless you have a closed container. So that is not an issue. So all you have to do is evaporate the water off, and you're going to leave behind the solid silver nitrate. So try not to overthink things. And this is just a simple, how do you separate it out? You're just going to evaporate it.